3 o'clock and it's a busy day today, so let's start. Can you hear me, Engine?
Yeah, yeah.
Great. So welcome everybody to the second routing working group meeting at IETF111. I'm going to welcome Engine again. Welcome, and it's great to have you as co-chair. And I would like to thank Chris Bowers, who's been a colleague for many years, and thank you again for everything you've done. And, we are going to progress. Not well. Please make yourself familiar with IETF rules and the fact that everything you share becomes property of IETF. And really short agenda for today is token cell routing by Stuart, functional addressing by Torles, and self-healing networking with slow label. There is no draft yet. Authors are working on the draft, so we made an exception here. The topic has been discussed in 6-man number of venues and actually being tested and deployed. So it's really exciting topic here. And Stuart.
Right. So asked to share slides. I'm going to share the TCR slides. TCR share. Right, thank you. So first off, there's a small error in that crept into the agenda. The draft is draft BCX RTGWG TCR 00. So what was our motivation for doing this? Right, new network demands stress the existing data plane protocols. Things like collection of telemetry, path guidance, reroute protection, the incoming need for SLOs, things like proof of transit, extensibility, programmability, etc., including parameterized functions. So we put together a sort of concept as to how we might design a protocol for to address these needs, in particular to support multiple features concurrently. It's easy to add one feature. It's more interesting if you want to add multiples. The need to authenticate metadata at intermediate nodes, and the need for extensibility in the design. So the basic idea is to construct a packet out as a lightly structured set of tokens. Tokens as in computer science tokens, not token ring, and cells as in we make up a packet as a number of small components in the same way that the human body is made up of cells. We apply longest prefix matching engines to invoke code points. Tokens we can combine to create more elaborate and interesting functionality, and we explain some of this in the use cases. You can stack the tokens for per segment and per node behavior where needed. So it's intrinsic. You should think of a token cell as a Lego brick, and a Lego brick that has parameterization of the cells. And we complement the cells with cells that contain metadata and security support and some interesting parallelization stuff. So the key differentiators from packets as we've designed them in the past are that we deliberately allow structured non-linear parsing, non-linear as in streaming media. So you don't have to go from one component of the packet to the next, and you don't have to deduce what you're going to do. The packet will tell you where you need to go next at this hop in terms of where you need to go in the packet next for processing. So we support programmable behavior at multiple levels in this approach. We construct a packet from the tokens, and then we combine them to get the defined behavior, and then we parameterize that behavior. This will become quite clear and obvious in the next slide. We have some tokens that specialize in things like security. We have tokens that specialize in scratchpad. And another thing that is of interest, although we have presented this as a packet design in its own right, I believe it's also an interesting method of describing advanced functions for extending existing protocols. So it's quite a good ancillary data or metadata design structure. So here's a packet, preamble, a few bits and pieces of housekeeping, and then it's just a series of token cells, as many token cells as it needs to define what is to happen to this packet during its lifetime across the network. One of the things that we thought was that actually the payload may exist in a token cell. So why would we put the we can clearly put the payload on the end of the packet if we want to, but why would we want to put the packet in a token cell? Well, there are some thoughts in the research community that you might want to modify the payload as the packet goes through. For example, for congestion management. For example, so instead of throwing the whole packet away, it may be that in certain applications, it's acceptable and desirable to throw some components of the payload away. For example, think about elements of a video system, for example, where you may be able to dispense with some bits, but other bits are important. This is an optional approach. Of course, we may have packets without payloads anyway for OAM purposes. So, right, this is one of the key slides, right? So, what does a token cell look like? It has a length because unlike, for example, MPLS, each cell will be variable length. It has a pointer to the next token to process at this hop after you've processed this token. So the idea is we chain these tokens together to get the functionality we need. And then we have the match zone. So the match zone is the part of the token that we put into a longest match engine. So that consists of two components. We have the cell type and perhaps sub ID, and then we have the prefix. So the prefix of the token cell blob. So this is where the parameters go. So think about this, for example, this might be specifying an IPv6 address, and then the prefix might be the IPv6 address itself, or it could be the IPv6 address itself concatenated with a more sophisticated programming parameter in order to do something a little more sophisticated than IPv6 network programming is doing by having a more sophisticated parameter in there that you look up in the lookup engine. Of course, you may discover that it's adequate to simply look at the token cell type, and in all cases, once you've done the lookup, you now know the structure of the suffix. So what's happening is the front of this middle piece of the token here is vectoring you into some code like an MPLS label would. But unlike an MPLS label, the token carries a set of parameters that assist in the processing of the packet, the forwarding of the packet. It will be obvious from that what the lookup engine does. So the lookup engine looks up the token match zone, retrieves the forwarding parameters, which is what goes on in any forwarder, and then vectors to a piece of code, which is actually what goes on in a forwarder, and sucks in the parameters it needs to create the effect. The effect may result in storing some information in the pipeline for the next token. So what sort of token cells might we have? We might have a forwarding one with the addressing type. We might have metadata, scratchpad. These are writable areas of the packet. Some security tokens. We think we can do some quite interesting parallel processing if the hardware can support it. So we have this concept of a manifest, which is the set of things to process in parallel, and the inverse of the manifest is the rendezvous, where we can bring them back together. Disposition. Disposition is what you do when the packet needs to leave this part of this zone, if you like, of TCR, this segment, if you like, in segment routing. And what at the moment what happens is a lot of this is deduced, but we think we can be a lot more specific with some parameters. Directives, for example, specifying some latency objectives, conditionals, and basically anything else that you want to program into the system. So let's look at the parallelization thing, which is novel. This looks complicated, but what we're really doing is exploring the properties of this concept. Whether you would build this or not would depend on your application and the capabilities of your forwarding hardware. But it's always interesting to look at what the natural consequences of the design are. So the first token takes you to a manifest. Manifest says there are 3 processing streams that you can do in parallel if you have the capability. So we process 1, we go to 2 in parallel with 3 in parallel with 4. 2 completes and takes us to 5. 3 completes and that's the end of the action series, and 4 takes us to another manifest with 3 more parallel actions and then a terminator at 9, and you're terminated when 5, 3 and 9 are finished. Now and 6 and 8. So this is conceptual, right? This is just to show you what you can do once you start putting pointers into packets and building some of the structures. And if you look below, I'm not going to go through the detail, but if you look below, we can see how we can chain together the structure we have here by putting pointers from one token to another. Well, this is the inverse function where we are rendezvousing, because it's possible that you want to do that it's quite good to do 2 and 3 in parallel, but you can't proceed any more until they've both completed, for example, to get to node 4. Again, I'm not going to go into the details. The slides are fairly straightforward, and there's quite a good description, I hope, in the draft. Disposition. So this is what a packet is to do when it leaves the network, and we know we already have this, and we have a need for this. It's the things like the next header in IPv6 that says what follows, the MPLS bottom label for things like VPN and pseudo wires, and more recently the network programming IP suffix, which is being used to specify what you do when the packet leaves the SR domain. Now, the interesting thing here is that we don't have constraints on size, and we have the advantage of more and flexible parameters if we take a specific disposition approach rather than an implicit disposition approach. So let's look at some packets. So here we have the first token, first active token is saying forward towards this IPv6 address. Notice that the source addresses are optional, because we know that, for example, in transport networks, you don't often need them, and you can consider them a payload parameter. We have the first token is the IPv6 address that tells you how we're going to forward, but there is a pointer to the second token, which is telling us to look at some SLO parameters. This packet must not arrive before this time. This packet must arrive in a window. This packet must arrive at a precise time. So this is a way of doing latency-based forwarding. When the packet arrives at the destination address, then we see we have the disposition token, and that tells us what we're to do next with this packet, how we're to process this payload and dispatch the packet out of the TCR system. Right, well, that's simple and straightforward. Now let's apply some fast reroute. Well, the first thing you'll notice is that for the fun of it, the first, here to the right-hand side in light blue is the packet you see above. And what we discovered, there was a failure and we needed to push a fast reroute token on the front. That's in dark blue. You'll notice that if it's more convenient to us, we can use a different address family for this. I mean, I've arbitrarily picked an IPv4 one, but the important thing here is that we're not casting the address family directly into the packet design. We are allowing the packet designer to consult with the network operator and use the addressing family that's most convenient for this function. Now, normally we would just push this on and do our best with fast reroute, but of course, if we're doing latency-based forwarding of some sort of SLO forwarding, we would really like that the fast reroute system took advantage of this and knew the history, and we can do this by pointing the next token, the red next token, to exactly the same SLO characteristics as was used on the main path. So now we've added a controlled latency system to fast reroute. So what about segment routing, right? So segment routing is pretty simple, right? You just have a set of tokens, one for each segment, and then a disposition token. Supposing we want to do latency-based forwarding with segment routing. We can do this by having each of the forwarding segment tokens take as a second action the latency-based forwarding parameters. So you'll notice that these first two segments are using exactly the same SLO parameters. So you can accumulate the same behavior and the same sort of timekeeping across each of the segments rather than doing it individually. Equally well, if we want to, we can have different SLO characteristics for different segments. So these first two here point to this second SLO characteristic, and this token N points to one of its own. The point here is to illustrate the power of the technique, not to suggest that every one of these techniques will be applied to every packet. How about some telemetry? Well, I think you'll probably get the picture straight away with telemetry, right? So we can do hop by hop telemetry simply by pointing the next token pointer to the telemetry information. And similarly, we can do the same thing with a manifest. So it could be that you want to do some quite sophisticated and complex data collection. Well, you can do your forwarding lookup, which in most forwarders is a DMA action, in parallel with doing your telemetry action, and it will be a simple exercise for the reader to see that you can clearly put all of these together, and which we do here. I'm not going to go through that in detail here, but I think you'll find all the pointers are right, and I would ask you to look at the draft and consult the slides and see how the pointers allow you to construct these sorts of structures. Authentication and security. What you can do here is, and there's some slides that that I'm going to incorporate into the next version of the draft, that show how you can break up the signature domains so that you sign the bits that are associated with a group of tokens or a set of parameters associated with a token, and how you don't have to sign the whole of it. You can sign the bits that are relevant for this set of hops and this particular action. So what we got with TCR is a general purpose network data plane protocol with serializable and parallelizable characteristics. It's the serialization and parallelization. It's the ability to introduce scratch pads and metadata. Scratch pads are information where the packet forwarders write as the packet goes through the network. Metadata are additional parameters or ancillary data that is needed to qualify how you forward the packet. It's an extensible approach, and it has differentiated security. You can apply multiple levels of programmability to this concept. You can clearly combine token cells into a packet and link them in different ways. You can provide parameters into the token cell, and the understanding of those parameters is implicit in understanding the cell and being vectored to the code that executes that cell in the same way that an MPLS label vectors you to some code. And of course, we can introduce new token cell types without needing to rewrite and redesign the protocol. So we would like to take this idea further to explore the potential of the concept, and certainly we would be really interested in working with anyone who is interested in exploring where this can take us. And that's the end. Thank you. Questions?
So I see a lot of discussions on the
right, I'm
window.
not looking at the chat. Yeah. Are there any that need comment now?
Torles, you wanted to talk? You disappeared from the queue.
I think Torles
will get the slides. I just pressed on the slides, but
Jeff?
So Stuart, I'm going to say one thing that is the biggest thing I want to say out of this very large proposal. What sort of network processing device are you expecting to consume this stream?
Well, we think that at medium speeds, an existing one could do this. There's nothing in here that you can't do with the existing hardware. It depends how many tokens you're going to have, but fundamentally, this is a sort of a hybrid between what goes on in an existing between MPLS and IP in terms of basic forwarding, and looking at the follow-on tokens is not particularly different from parsing an ACH, and everyone is now looking at ACHs and metadata and ancillary data. So this is kind of a different way of putting that together in a way that I think is more powerful than some of the other techniques we're looking at.
So while I agree with you, I'm going to leave you with two comments. The first one is this somewhat resembles the work that firewalls have to do with a given firewall program to implement its intent for a given set of instructions. And we know that long chains can have negative impacts on forwarding rates. And the second comment is, much like the firewall problem, you're now introducing a programming path that now has a lot of exception paths that need to be considered. So when things can't run through the program appropriately, figuring out what that actually means for the data that's being carried becomes a lot more exciting.
Yeah, I kind of sort of take the sort of, because I come from the MPLS school of design, I kind of assume that if you shouldn't be putting a packet through an LSP or whatever, a token switch path, I suppose, unless you know it's going to cleanly get through there, because you know from the routing system what the capabilities of the path are, and so long as you design the thing right in the first place, and we have a lot of experience in MPLS of designing these things right in the first place, it will work. And if you screw up, then the usual thing is just to dump the packet and increment a counter. So I'm not too terrified of this. It's certainly very different from things we've tried, I think, in the past. But we're sort of getting close to that with the ancillary data and the extension headers that we're doing, because they have lots of undefined states, and they're even less defined because you're doing implicit ordering rather than explicit ordering of what you need to do to the packet.
Okay, thank you.
Anyway, if it's not quite a TLV based system, Tony. I think we can make this run much faster than TLVs.
Stuart, so we are going to publish the comments here on the list as well. It would be great if you could read them and address them.
I will do my best to answer them if you can capture them in some way that I won't lose them.
People are always skeptical. New ideas.
Yeah, and this is a concept, right? What I'm trying to do is to get people to understand the sort of power you get if you put pointers in a packet rather than rely entirely on implicit parsing, because no one actually just looks at the front of a packet anyway, do they? They're going to have a look inside all sorts of things to try and figure out what to do. So this is moving from implicit parameters to explicit parameters. Okay,
so we've got 1 minute. If there are any short questions, comment, please go ahead. Otherwise, we'll move on.
Are you working on the queue as well, or only on the chat queue?
I can work on either, whichever you want to ask. I'm having trouble following both of them in parallel.
Well, I think maybe just one marketing for you, right? Given, I guess, fair to say, a little bit of the history and adjacency with MPLS. This is also discussed in the open MPLS design team, which is meeting regularly. So there is another great chance to join that effort and maybe have the discussion over there if you haven't been watching that space yet here in Routing Working Group.
Just to answer Robert's question, there is a TTL. I didn't show it. It's in the preamble. So there's a bunch of stuff on the left I always show, which has got a small, tiny number of parameters that are always pushed onto the front of the packet, and one of them is TTL.
Start. Maybe you can stop sharing. So,
all right, okay, I'll
yeah.
stop sharing. Thank you for your time.
Thank you. Thank you for presenting. We will take it to the list. It's a short meeting today, and we've got a lot of information to present.
All right. So this is an idea, born from similar intentions. What Stuart was talking about with a terrible name. There have been, in int area and in routing working group in the recent past, a couple of, discussions and proposals about introducing variable long addresses into, an extension or an evolution of IPv6. And I wanted to basically look into what might be not well explored benefits, because driven by one of them, the idea came up, and then it basically felt that it also was very good to improve on some of the very well understood and explored challenges that we may have. And so the problem space is that of limited domain networks, and I was already presenting the problem space into IoT Ops on Monday, not the solution. So maybe the document is also getting split up between the problem and the solution. And you can see from the slide that the core issues such as efficient. Traffic steering, like SR does it, should be very simple with this and more efficient than maybe many of the Spring CRH variations. It should support equally very flexible programming in the way that SR v6 adopted that with SRH, and then also by value of having variable long addresses, it would be easily feasible to introduce new semantics that need longer addresses, for example, and of course research. But let me start with the new problem space that I think with IPv6 we've mostly ignored, which is the fact that the IETF network protocol iceberg is pretty much 10%, which everybody talks about, which is the internet, and then 90% of what since RFC 8799 is called limited domains, or the people called it private networks, many of them in the IoT space, manufacturing, energy, oil, gas, transportation, constrained networks, but equally, service providers, infrastructure network with IP MPLS or IPSR is not, quote, the internet. It just, has the internet running on top of it. So that I counted all the devices on the planet, and 90% of them are not on the internet or connected to the internet, but really just within these private networks. And so then the question arises, how good is IPv6 and IPv6 addressing for those type of networks? And given the time limits, I won't go into all the problems, but I've kind of summarized a couple of them, starting from PD to PI space, ULA space, which especially through the work that I did in Anima, I learned more than I think I wanted to know about it. And then also the retirement of site local addresses, which was done in general, but not for multicast. So there's really a lot to be said about a lack of IPv6 addressing to better support this. So, and the example that I wanted to bring up from industrial, but another space as well, is that you want to be able to build, embedded constrained networks whenever you like, without having to bother about a single global address space, but just about your network local address space, and then compose and interconnect them in an arbitrary hierarchy and topology that you want, right? You may want to start with some form of machinery that you're selling, which has an internal Ethernet network and a router to the outside. You assemble these to form some larger machinery and ultimately an assembly line. So multiple hierarchies to even get to a single building block that's shown here. And then you can easily imagine how many of these building blocks here on that picture might need to be interconnected in a way that's certainly not the, I just need a flat, everybody can reach anybody else network, but we already, have done good standardization with things like MUD and other mechanisms to really ensure the security of these type of networks. And as it turns out, what's going to be proposed is just, going very nicely along with it, I think. So here is a typical classical example of these instances that you can even see in industry standards. I've worked in transportation with trains and so on. So if you look at some of the standards for how to build networks in a train car, or any other example machineries, what you typically do is you're using the wonderful RFC 1918 10net space. Every instance of a product you're building has the device has been given exactly the same 10net addresses. And then you have a gateway with NAT, like any, industrial Ethernet switch. You're looking at that and you'll see that, oh, well, why does it have this strange form of NAT? Well, because exactly of this type of use case where, for example, netting the third byte of the address to be unique on the next layer of LAN, which is the orange level. And then you have the second byte where you can do one more level of aggregation with this existing IPv4 addressing space. And voila, that's basically a lot of what you do for security and combination. You're constrained to two levels. You may go up to another IPv6 level on top of that. But if you really compare ULA IPv6 with this stuff in IPv4, you have the same 16 bits really available, but you have additional problems with IPv6 ULA because, supposedly NAT is evil and you shouldn't use it. And then you run into hash collisions. So here, let me go over to the solution to spend most of the time on it. So in the example pictures I'm going to give, addresses are going to have length modulo 4 equals 0 and prefix length also the same. So effectively hex string addresses like an IPv6 with any boundaries on 4 bits, so that I don't need to cut in a single digit. And then dots are just, structural, optional things just to visualize where the structure of an address ends. So the address allocation within a single network, that's kind of the one core new thing that we haven't, in normal networks in IGP expected, which is that every assigned prefix has to be non-overlapping with any other, so that anybody who owns a prefix owns any longer address of that, which is basically crucial to allowing this to work. And yeah, that might actually, when we get to actual routing plane for this, might be an interesting question about the consistency requirements that we want to raise at the distributed control plane. Yeah, and then we just expect that, let's say for now, everything is routed in the IGP like host addresses, right? So everybody can route to anybody else's unique prefix. So here is then the example. So we have one network, network 1, and a couple of devices interconnected with each other, each one showing its own prefix. And then basically somebody else builds a second network, probably following from the same industry standards, slightly different mirror topology in this case, but certainly, decidedly or unintentionally overlapping address. And now the question comes, okay, how do you start connecting this and allowing to have traffic flow between them? So, and here is basically the simple summary what you do for the interconnection, which is that, one network wants to get connected to the other one. So on that network, which is the blue one, network 1, you're starting to establish some connection into the other network, which is shown here with these dotted boxes, right? So you take RA and you connect it into LAN 1 on the orange network, and you do receive a particular prefix from the network 45, likewise with RB, right? So you don't even have to have a symmetric thing. It's good enough that only one network wants to connect to the other and connects as if, it has just connecting normal nodes to that network. So, and then is the very simple address processing that we're doing when passing the traffic on, which is, and given the time, I won't be so slow that everybody gets in the first run. Took me a while as well, but you go from the source, and the destination address is 22135, and the source address is your own 52. So the first two will route it to RA, which is the address of that node in the blue network. The second two is the function of the remainder of the address, which in this case would be, put it into a different network, and locally the network connection number, let's say 1, which is the parameter, which is the third part. So, and what ultimately happens is that RA is knowing, okay, I need to put this out on the link into network 2. I'm going to strip this whole prefix, and I'm recirculating the network, the packet into network 2 routing and forwarding. So it's going to be forwarded to number 35. And then, the reverse thing is happening optionally with the source address, where we're basically prepending the return path, so that if when the packet ultimately arrives at destination 52, it knows how to send return packets back to the 52 in network 1. So what is that? It is in the forwarding plane exceptionally simple, I think, when we want to start having this type of interconnection with, every network having its own address space independently. It's just normal prefix lookup like we've done it forever. And the only novel things are stripping and prepending address prefixes. And when you're doing this function, recirculating, after that operation. So it's stateless or prefix address rewrite. So if we're looking into any type of address rewrite option, to connect networks, it should be the best scalable performant option, right? And as should be not too difficult to see, it would be possible to make that work for an arbitrary topology interconnect between these hierarchical or any type of mesh. Now, that was kind of the most complex thing. Now, when you think about just the logic of an address being, a sequence of functions, and each function being, let's say, either a semantic prefix or a node prefix, followed by a function code and a parameter, you can see that this simple, I get a packet, I do a prefix lookup, depending on the prefix lookup, I have an adjacency that does different things, can map into the most fundamental functions that we already need in routers and would like to be more flexible, right? So let's say the function number 0 followed by a value for the next protocol is simply the host stack thing, right? So would allow me to eliminate the next protocol field from an IPv6 header because it's simply in the address. Number 1 could simply be steering, which basically then is followed by a node prefix. So that would be a replacement to what we're doing in SR-MPLS or SRv6. It's all in the address. It's just a sequence of steering instruction, node by node. And as you can see, the address space that you allocate for steering hops can obviously be a lot shorter than 128 bits. So it would be a very compact encoding for the steering. Number 2 was the instruction for this internetwork where you're stripping and adding addresses. And of course, you can come up with any other functions and parameters, which is, for example, how you could map any of the programmability in SRv6 that SRH has into the address equally well. But given how it's all variable length, you don't need to waste 64 bits when you don't even need them, like in most cases in SRH that we have now. And if instead of a node prefix, we're saying, well, let's just start with a semantic prefix like we have in IPv6 as well for example, multicast addresses, you could equally, map any future semantics that you want to have into the same address space. Just make sure it doesn't overlap. We've done it so far with standards-based prefix allocations. I'm saying in general, this could as well be done through, configuration programming of the forwarding plane from the control plane.
So let's check 2 minutes, and we are not going to go over time.
Yeah, okay. Right, so the control plane, I think there is a lot to be said about how do we get, know how to get to a destination. I'm making a lot of cases for many private networks not really having to have other naming because within a network, these addresses are fixed for lifetime. So they wouldn't be location dependent within a network, and the path to other networks equally can come from PCE controllers. But otherwise, there's obviously a lot of interesting extensions for path routing that we already know how to do with BGP, for example. Here is, an example of how simple a base header could be. So this would be, how to take IPv6, strip everything that we don't think we need, and arrive at a much simpler header, destination address, source address. We need length for both of them. I think we need ECN and hop limit. Everything else can go into extension header. Obviously, this would require a newer version, not 4 and not 6. So, it could basically be done in a backward compatible way so that it's a superset of v6, but that details haven't been talked about. So, I think, to come to a funny end here, I think what we're talking about really is if we want to think more about addressing and not only, tag on more and more extension headers, but think about the basic addressing that we have. We have gone through a long evolution, which started with NAT, 26, IPv4 to IPv6 transition mechanisms. Most of them, I think people would find, not very good, but some of them actually could be domesticated and become kind of really useful functionalities, which is, I think, what we're doing here. We also have functional structures on IPv6, scopes, zones, unicast, prefix, multicast. A lot of the things we have done were ad hoc things, on top of IPv6, not very structural. We have done a lot more structural stuff on the address processing in MPLS stacks and source routing in SR. Those things also, are nicely flowing into this. So I think when we take all these things together, this proposal really, should give us a very nice multi-purpose functional address processing architecture. And that's it. Questions?
We are going to take one question here, if any.
Edward?
Okay, Edward.
I have a small question about the redundancy, resiliency, because if node and if link for gateway is encoded inside the header as a part of the address, and a particular node, a particular link would be down, then we need to find some route. But if it's encoded in the IP address, does it mean that we need to change IP address or IP?
Yeah, exactly. I think one of the things you would obviously do in this case is also to have anycast addresses, which you assign to more than one node.
Okay.
So you're going to a logical, exit node address.
We are going to stop here and move to the next.
Thank you very much.
Thanks, Torles, and I would really encourage you to send your questions and comments to the list.
Will do.
I see the slides, don't hear you.
Can you hear me?
Yep, please go ahead.
So I'm Alexander Azimov. I'm working for Yandex, and since we are running out of time, I'll try to do it fast. And so we will try to fast discuss the opportunity to enrich TCP with self-healing capabilities. I will start my talk with focusing on the data center environment, but as you will see, it's not only about data centers. Here, so here is a typical topology of the data center. There are top-of-rack switches connected to the first-tier spines, which are represented here with literal S. The set of top-of-rack switches connected to the same first-tier spines represent a point of data center or pod. And there are super spines that interconnect different pods, which are represented here with a literal X. Of course, load balancing is widely adopted in such topology. Normally, it's equal cost multipath with a hash function using 5-tuple. So modern data centers provide multiple paths between most of hosts. The single path between two hosts exists only inside the rack. Inside one pod, the number of paths equal to the number of planes in the data center. In the case of interaction between pods, the number of paths will be the result of multiplication between the number of planes and the number of super spines in each plane. To make you feel the numbers, here is an example from one of Yandex data centers. It has 8 planes with 32 super spines in each of them. This makes the number of paths in the case of intra-pod interaction equal to 8, and in the case of inter-pod interaction equal to 256. Yes. One may expect that this number of paths should provide fault tolerance out of the box. But the real outages in the data center are way more complicated. Let's say we have an outage and at one of our super spines, X11. And unfortunately, this outage doesn't affect the control plane, so BGP keeps running. But there is constant packet loss. And since the majority of our traffic is TCP-based, we have to rely on its loss recovery mechanism. There are two main options in TCP for loss recovery: selected acknowledgement, and a retransmission triggered by RTO timeout. But all these retransmissions will have the same 5-tuple, so they will all travel the same path, resulting in service degradation. And as the congestion window will be shrinking, it will increase the chances to meet RTO event. And continuous RTO events is a disaster inside the data center. RTO is calculated as the minimum from measured RTT and RTO mean. The default Linux value for RTO mean is 200 milliseconds. If we are unfortunate enough to lose a SYN packet, the basic timeout is even higher, it's 1 second, while real RTT in the data center is about 1 millisecond. To make it even worse, it increases 2 times after each unsuccessful attempt. Network outage in the DC of course, ends up when the broken device is shut down. But all the time that it takes to collect data and debug the issue, there will be continuous service degradation. The question is it possible to enrich TCP with the opportunity to jump from the failing path? To answer this question, we'll need to take a tour through the Linux kernel manic list. It was 2011 when RC 6438 was published, where it was stated that flow label can be used to balance encapsulated traffic. The idea is simple. Since the transport layer may not be available, we can improve load balancing quality if we put the hash of the TCP socket in the flow label field. In 2014, it was introduced in the Linux kernel. Similar changes were applied to other encapsulation methods, such as GRE or UDP. But the progress in the Linux kernel hasn't stopped at this point. Instead, it was progressing far beyond IETF documents. The next year, there was another patch in the Linux development, which added TCP hash recalculation upon negative routing event. What is negative routing event? It's RTO timeout that we just discussed. And next year, this behavior was further strengthened. Since this time, the hash is recalculated on both RTO and SYN RTO events. And as we discussed, RTO timeout affects not only flow label value, it also affects all kinds of encapsulations. In the case of GRE, it affects its key field. In case of UDP encapsulation, it changes the UDP source port. And a surprise, it has become a default Linux behavior. And as I have already mentioned, there is no corresponding IETF documents. But how has it changed the life of TCP flow in the data center? Once again, let we have a partial outage at X11. This time we will also add the flow label to our hash function at the top of rack switch. In the case of selected acknowledgement, nothing really changes, but if we have an RTO event, the TCP hash at the socket will be recalculated, and so does flow label. So after each RTO event, we have a 50% probability the traffic will jump to another plane. The more planes we have, the higher is the probability that the jump will move TCP to the unaffected part of the network. And it is fully transparent to the application. In addition to the flow label in the hash function of the top of rack switch, we also deployed eBPF agents at the host to change the RTO mean values according to the real RTT in the data center. And here is the result of our experiments. We decided not to wait for the next big outage that will create a service degradation on most of our services, but to create a small artificial one, though on real production services. We took a top of rack switch and created a constant packet loss on one of its uplinks. The switch had 4 uplinks in total. On the left, you can see the outcome of the data plane monitoring. It is UDP based, and as predicted, it shows 25% of packet loss. On the right side is the traffic volume from servers, from the hosts behind this top of rack switch. The volume of the traffic has reduced 4 times. Now the same experiment, but with flow label enabled as the hash function of the top of rack switch. The UDP-based data plane monitoring shows the same result. It's just UDP ping without any retransmissions. But TCP flows of our services are jumping from the failing path, and service traffic is preserved unaffected. For me, it looks great. So, what one can learn from these slides? Using flow label at the level of top of rack switch and maybe first tier spines gives a TCP over IPv6 a self-healing capability. To make this jump of traffic quick enough, you should also use eBPF to change the RTO and SYN RTO values according to your latency. And this goes for free, though with poor documentation. And one may note that an environment with multiple paths is not limited to the data center. One may say that the internet itself consists of multiple paths between the majority of its points, and all this jumping from failing path to another may improve user experience in general. Here are again some real numbers from Yandex Network. Less than 40% of prefixes that we are receiving from our peers have only one best path. The average number of best paths is about 4, with a maximum of 44 best paths for the same prefix. And here's an example of a real outage. As you can see, 2 of the 5 best paths were not affected by the outage. So it leaves the door for the jumping from the failing path. So is everything works that great? And do we need only to properly document, implement it in the Linux kernel? Unfortunately, there was a trap. And this trap is called Anycast. In the DC environment, stateful Anycast services are not that, while in the wild internet, Anycast TCP proxies are representing significant portion of traffic volume. And unfortunately, this kind of services doesn't perform very well with Linux flow label mechanics. Let me show why. Let's say we have a client that establishes a TCP session with stateful Anycast service, for example, TCP proxy. And everything is fine until RTO happens on the client side. For example, if client pushes data to a storage, the RTO event is not that uncommon. But RTO at the client side also triggers TCP hash recalculation and thus generation of new flow label. As a result, subsequent packets can be redirected to another instance, which won't have any appropriate state and will drop these packets accordingly. These might be following RTO events that may return the traffic to original instance, but anyway, it won't improve user experience. And this is no theory. We faced this kind of behavior with our users and had to switch off flow label at our border routers, which partially improved the situation. By the way, hashing with flow label is Juniper default behavior. And if you have seen a greater number of TCP connection timeouts in IPv6 compared to IPv4, now you should know why. The scenario for the SYN RTO is a bit more complicated. Let we have a SYN packet, and this time it is correctly delivered to the proxy instance. But the following SYN ARC packet is lost. In this case, we will have two sides, the server and the client, trying to retransmit SYN packets. So after the default SYN RTO timeout, which is normally 1 second, the client will send another SYN packet with a new flow label value. And it may reach another instance, but not. But now we will have one client and two servers trying to establish one connection. Which leads us to a race condition. If the SYN ARC is received from the second proxy, everything will be fine. But if we receive first the SYN ARC from the first one, we are meeting a peculiar situation. The client needs to respond with an ARC to finish the connection procedure, but it has flow label that directs packets to the second proxy and the acknowledgement number related to the first proxy. Of course, such scenario will end up with connection timeout. In such race condition, such a race condition is likely to happen? It's really hard to say at the moment because it's really hard to check how many such connections are broken. But both issues with RTO and SYN RTO may happen only if the hash is recalculated at the client side. And this provides an opportunity for a quick fix that will still save the improvements in case of the outage and resolve the issues with TCP session timeouts. So If we just restrict hash recalculation upon RTO events at the client side, while keeping current implementation for the server side, it may become a proper default behavior. And it should have a knob to enable it on both sides in the controlled environment, where because in the controlled environments, we can assume that we can distinguish where is the anycast service and where is the unicast service. So in the IPv6 world, we have an opportunity to enrich TCP transport with self-healing capability. Most of the mechanics are already in place, and today it works in the data center environment. Though we need to change the Linux implementation to guarantee robust behavior in general. And this time, as a community, we need to properly document it. There are several open questions. For example, should we focus on TCP only or try to provide a general guidance? There is also a number of confusing documents related to the flow label that don't work with Linux implementation. And these issues should be, of course, addressed. So if you think it's worthy and you have a desire to assist in this work, feel free to contact me. That's all for me. Thank you. Any questions?
Can you go ahead?
Oh, I'm just switching my hand off. A substitute for clapping. Very good presentation. Thank you.
Thank you very much.
Ready?
Hi, Alex. Yeah, I agree. It is a very good presentation. I had a question. Is the insertion of the flow label done by the first hop router / Tor switch or in the Linux kernel itself?
Can you repeat the beginning of the question? So are you asking about where is the hashing is implemented, or who is changing the flow label?
Who's
You
changing
need to observe RTO in order to be able to do so.
Yes, the flow label is changed at the host.
As a host, okay.
Yeah. So today it is changed on the host upon the RTO events, both RTO for the established TCP sessions and upon the SYN retransmission.
Okay, thank
However,
you.
if you think of the cases where overlay starts on the Tor or first hop switch, nothing prevents us of copying flow label into overlay hash, or not copying, but at least including it. So it would be evenly applicable for EVP and like cases. So there's no more questions, and we are running out of time. Speaking
Alex,
of,
did Alex write a draft on this, or is this just a presentation?
At the moment, it is just a presentation. We are still at the beginning of the road and discussing a proper way how to fix it. And then there will be a lot of work must be done in the IETF documentation, as I said, because we need to update the documentation for the flow label itself, and also write a spec that will describe how the hash recalculation should affect the corresponding parameters, including flow label.
Okay, thanks.
Kirati, so the plan is to provide routing as a home for this work. And so Tom and Alexander are already working on it, and so more people are more than welcome here. The problem is real. It provides real solution to serious issues, and I would like to thank Alexander for the presentation, and again, please reach out and contribute. My wish is to have something similar to 7938, which is BGP and RGC, which has become de facto cookbook for hundreds and hundreds of people building networks. So I'm really looking forward to work here, and thanks for doing the presentation, doing the work. We are completely out of time, so I would like to thank everybody for attendance, and I really, really hope to see you face to face in Madrid. Take care, everyone, and have a great day.
Yeah, I just want to mention, this is one of the examples that although you don't have a draft, but you are presenting something useful for the community, we are also welcome you. That's it. Okay.
Thanks, everyone, and see you at IETF 112.
See you next time.